notice what I've done. Besides, well, two things. This is the key. So it's got all the answers in it. Plus, I've highlighted some of them just to keep me from wandering. And those are the ones I'm going to focus on simply because they're unique ideas. I want to make a point. If some of them are very similar to each other, I put both of them in there or three of them in there to make a point of their differences. But I didn't highlight all of them, just the ones that give us a unique perspective on the material. And so we can cover all the topics and then maybe stimulate some questions if you have problems. That's the purpose. Okay. So I can see it too. I can look at it here, I can look at it there. Okay. So let me scroll up a little bit. We get the first two questions. I want to introduce a topic. Some of these are just straight memory, right? You just question and you give me the answer. So those will like take 5 seconds, but some of them take a little longer. And you'll notice that I've structured this document so that it's like an exam. So the exam will look just like this, only it won't have 205 questions in it, a lot less. This is just to give you practice, to emphasize the second part of your best friend idea, boredom. Right? If you work all these, you should be bored by the time you get through with them. Okay, first one. Which of the following is an example of a quantitative observation? Right? And the difference between a quantitative and qualitative. Quantitative, you usually think numbers. Right? It's a numerical measurement of some kind, that observation. Whereas qualitative is more generalized, and it could be just a comparison between two things. It could be an observation of a general property, like a color or general size, something like that. So in order to be a quantitative observation, a piece of metal is longer than, no, that's qualitative. A solution 1 is much darker than, qualitative again. The liquid in beaker A is blue, we're qualitative again. We get to the temperature of the liquid is 60 degrees Celsius. That's quantitative. So you can stop there. Right? We found our answer. At least 2 of the above are quantitative. Nope, just 1. Okay. Number 2. Oh, and I might also make this observation. We're going through these review questions, and I'm picking out some, but you should always have in the back of your mind, what if the question were changed around? Right? What if this type of question appeared on the exam, but it wasn't exactly like that? It might be a different answer. So you also want to not just pay attention to the question, but pay attention to the answers. And how could the question change to indicate a different answer? Okay, just a heads up. Generally, observed behavior that can be formulated into a statement, sometimes mathematical in nature, is called what? Does it say anything about why? No, so it has to be a law. So if that statement were changed to observe why, or it mentions the word model, then you're talking theory. Okay, just to illustrate my previous statement. That's a natural law. Okay, number 5 addresses the memory problem. of prefixes to the base units. What do each of these prefixes mean? So we've got, what do we have? Well, we know what the answer is because it's given there, right? But what does nano mean? Nano times the base unit would be 10 to the minus 9th. Okay? Milli. That's 10 to the minus 3. Okay? This is a billionth. This is a thousandth. Centi. That's 10 to the minus 2. Centimeter. A centimeter is 1/100th of a meter. And the last one, kilo. I think I made a point of this one last time. Kilo is 10 to the 3rd. So 1,000 times the base unit would be that derived unit of measure. And that's the order of smallest to largest. That's why A is the answer. All right. So number 6. Um, 8.1 kilograms. I should write I'm going to write up here, reference the number. By the way, I think these restart numbering with chapter 2 in the review, so I better put chapter 1 up here also. I think they start numbering over again when we get to chapter 2 problems. 8.1 kilograms contains how many grams? 8.1 kilograms equals how many grams? There are 2 ways to approach this, the long way and the short way. When you have something like this, where you have a base unit and a multiplier, and the answer needs to be in the base units, think of this as 10 to the 3rd, right, times 8.1. So that's your answer. Okay. Now, it won't always be that simple, so maybe you need to know the other way to do it. You can use dimensional analysis. Right? Kilograms on the bottom to cancel, grams on the top to end up over here. So this is 10 to the 3rd grams per kilogram. Now the kilograms cancel, you got 8.1 times 10 to the 3rd. Now this will work for any problem. This one is convenient because that little trick works, but maybe it won't always work that way. So you have that other option. Seven. Convert 0.3980, 0.3980 meters to what? Millimeters. Okay. You have 2 options here. Right? You can use the dimensional analysis, right? Use the units, meters, millimeters on top. Right? So how many millimeters in a meter? What does milli mean? Milli means 1,000th of, right? So if the size of the unit is 1,000th of a meter, it takes 1,000 of them to make a meter, doesn't it? So you can do it that way. And this times 1,000 would be what? Millimeters. Notice, as the unit gets smaller, the number gets bigger. That's a way to check yourself, to see if you're moving the decimal point the right direction. Because I've seen students go the wrong direction, like they'll move it 3 that way, and not think about that many meters can't be less or fewer millimeters. It just defies logic. So if the number gets bigger, if the units get smaller, then the number gets bigger. And that's a way to check yourself. Or you can say, use that principle and say, all right, it needs to move 1,000 times, right? Tens, hundreds, thousands, 398.0. And that's the right number of significant figures too, because this has 4, that has 4. Let's see here, 7. Am I boring anybody yet? If this is useful, we'll keep doing it. But if it's just, why am I here? Then we'll move on to something else. 9. What's the measure of resistance an object has to a change in its state of motion? Resistance to a change in state of motion. You can go process of elimination, right? Is it length? I don't think so. Volume? That's just a simple statement of dimensions. It's either weight or mass, right? So which one references the resistance an object has to a change in motion? Does it matter if the object is in a gravitational field or not, or if it's in a large gravitational field like Jupiter or a small one like the moon? To resist change? No. That's mass. Mass. And the magic word here is inertia. Mass is an indication of inertia. It resists the change in motion, whether it's sitting still or whether it's already moving, right? According to Newton's first law of motion. That's just to help you distinguish between mass and weight. All right. This is a good one, 11. All right. As a part of calibration of a new laboratory balance, a 1 gram mass is weighed with the following results. So we're taking liberties with the words here. It's weighed, sort of. We're actually determining its mass, right? But that's a holdover from olden days. I still say weigh something out on a balance, but I mean determine its mass. Anyway, so what are we looking at? We're looking at 3 measurements of a known value, right? We know the value of that mass is 1.000 grams. So if we look at those values, are they close to that? No, they're off by 20%. That's a huge amount, right? So the values, none of the values are accurate. They're all inaccurate. Right? So we know that they're inaccurate, right? Because they don't come anywhere near 1 gram. Plus, one thing that's given here that I didn't mention in the lecture was, let's take the first one, 1.201 plus or minus 0.001 grams. This plus or minus references what we know about the balance. Right? The balance has been calibrated at some point in the past, and we know that it gives us reliable results. So when we say that value, we know it's between the values of 1.00 and 1.02, right? Plus or minus 0.001. Okay? So because we know this, we know that it's way off because it's more than that value away from this value. Okay? And all of those values are way off. They're a long way from this plus or minus from that value. That plus or minus doesn't get it anywhere near this. So we know that all of those measurements are inaccurate. Right? So that's accuracy. How about precision? What do we need to know about precision? What's the grouping? Right? So the grouping is 201, 202, and 200. and they're all plus or minus the same thing. Right? So we could just look at those values and say, yeah, they're pretty close together. I mean, they're just off by 1,000th. Or we could say, all right, if this one is somewhere, it's either 0,0 or 0,2, right? 0,0 or 0,2. This one is right in the middle of those two. So that's another indication that we've got a good spread. So that is precision. This is precise. Okay. All right. So let's go down to these. These should be, we should knock these out pretty quick. I think there are 3 of them. No, there's only 2. We'll look at those targets. We're actually saying something about those targets it's actually, I'm repeating myself because we've already covered precision and accuracy, but these targets are another representation. So E, which of the following figures represents a result having high precision? That is good grouping. Both 2 and, yeah. 2 and 3. Yeah, 2 and 3. So that's why E is the answer there. And then which of the following concerning these figures is correct? Okay, so we've got to read through these. Figure 1 represents a systematic error, and figure 2 represents a random error. All right, what do I mean by that? Systematic, let's say this is 13. Systematic versus random error, types of error. Okay. Systematic is the type of error that can be predicted. That's what we mean by 1.201 plus or minus 0.001. We can predict that the value is going to be with some degree of confidence that the value is going to be between 1.200 and 1.202. That's a systematic error. Those can be easily corrected for and accounted for. Right? If our balance says 1.200 and we know the accepted value of that weight is 1.000, then we can say every time we get a reading of 1.200, we write down 1.000. Right? Every time. It's got that type of error. It's systematic. It's predictable. Random error is not predictable. It could be anywhere. And that's the one that gives researchers fits, because you don't know where it's coming from and you can't predict it. Okay, so based on these figures, which one is systematic and which one's random? Well, systematic error, 3 has virtually no error. But 2 produces a nice grouping. They're always off target by that much. That's systematic. Okay. 1 is unpredictable. It's all over the place. So number 1 would be random error. And
it would be hard to put not do E because E was so precise and accurate. It says
figure 3.
It's no errors.
Well, strictly speaking, that's not correct, because there is some error in there that you can see. The only way there'd be not any error is if the bullet entered the same hole over and over and over again, which is never going to happen. Not even for match grade ammunition. Okay. So that's 13. Let's see. 16 and 17. The amount of uncertainty in a measured quantity is determined by what? Well, let's see, what are our choices? Skill of the observer, limitations of the instrument. Looks like those are the only two that are given in different combinations. So what determines the amount of uncertainty in a measured quantity? Can you put your finger on one? No. It's always both of them. The instrument's going to have some inaccuracy built in, and the operator skill is going to determine the level of inaccuracy too. I used to use a piece of equipment that was $250,000. It was analytical equipment that would tell me how much of each element was in a sample. We had to prepare the samples, all right? So the skill of the lab technician that prepared the samples was an issue, right? If they prepared the samples and they spilt one, didn't tell anybody, then when you dilute it up to a known volume, it's going to have less of the in that end sample. So the skill of the operator, of the preparer, and then the skill of the operator for the instrument. Sometimes they're the same person. And you always get better results from someone who's skilled in operating the equipment. Because there's a process you go through called calibration. Right? Each time you run the instrument, there's always the potential for drift of some type. And you have a set of samples, prepared standards, and you run those standards through the instrument, and it associates a given concentration of an element with the signal strength. And it does that for 3 or more, usually 5 or 6 of them we used. And then it draws a calibration curve. So it knows that if the sample goes through with a signal of this strength, it correlates that to this concentration. And if the operator, the preparer of the standards is kind of squirrely, they're not going to be good. But the instrument, actually, the accuracy of an instrument performing a certain type of operation is highly dependent upon the expenditure in purchasing the instrument. So $250,000 says it's probably very accurate instrument. You could do the same thing with an instrument that costs 1/10 that much. And I've done that. But you have to be more careful, and it doesn't measure to as many significant figures. Okay, so the answer to that one's A. Both the skill of the operator and the instrumentation are limiting factors on the uncertainty in the measured quantity. 17. A scientist obtains the number, 450067. 450067, and then we have a couple before that, don't we? Nope, just one. Sorry. Here we go. Now, okay, so if you've determined that you're only allowed 4 significant figures, what do you do with it? Right? So you have to decide which are the significant figures. Right? Are they significant? Leading zeros are never significant. How about these? Yep. Captive zeros are always significant. How about these? Only if you have an explicit decimal point. So they're significant too. So we're starting from here. 1, 2, 3, 4, right there. This is greater than 5. So this one has to be 1. There you go, 04501. Okay. Let's see, is this different? Oh, scientific notation now. 20. So we want to express that number 0.0810. 0.0810 in scientific notation. Right? What are the conditions for scientific notation? Right. You need an exponent of 10 that's derived from that number, and the coefficient of the number has to be between 1 and 10. So if we move the decimal to the right, 1, 2, that puts this value 8.10 between 1 and 10. So we're good there. But what's the power of 10? Well, when we move to the right, we're storing up small values into a larger value, which means this has to be a negative power. Right, we're going from small number to large number. That means the power here has to be small. So we moved over twice, didn't we? 8.10 times 10 to the minus 2, and 3 significant figures, 3 significant figures. Right? Those first 2 zeros are not significant. So that's why the answer is D. We're going to go back the other direction for 21. Let's just put it up here. 21. All right. This number, 6.49 times 10 to the minus 3, and we want to express that in decimal form or standard notation. Right. So which way does the decimal move here? You're taking this small multiplier and putting it back over here, which means the decimal has to move that way. You got to make this number smaller as you put this information back into it. So let's make room here. 6, 4, 9. Starting here, going 1, 2, 3. There we go. And we still have 3 significant figures right there, which means A is the answer. 22. Express this number. All right, so similar idea, only now 237. The power of 10 is positive. So we're going to take this large number and embed it there, which means we have to move the decimal to the right to make this number larger. 2, 3, 7. 1, 2, 3, 4. No decimal point. Why? Because 3 significant figures, 3 significant figures. If we put a decimal here, we're claiming an extra 2 significant figures that we didn't have to start with. Okay. 22, 23. Yep, 23. Let's make some room here. Oh.
On 19, it says express that one number in exponential notation. What's the difference between exponential notation and scientific
Yeah. In your author's minds, authors of the book, there's no difference. But there is a difference. Exponential, you can have any exponent of 10, and the coefficient could be any other number. It doesn't have to be between 1 and 10. In this case, it is the only option you have. Let's see. Let's do it. 165,000. How many significant figures? 3. 3. Okay, so our understood decimal should go 1, 2, 3, 4, 5 if we want scientific notation. And 3 significant figures in both. So let's see, is that one of the answers? Yeah, that's a selection. But what if we did 165 times 10 to the third, like moving 1, 2, 3? That's one of the answers too, isn't it? All right. So that would be a bad question on a test. Because exponential notation, you could put either one of those. You couldn't put A because you're claiming more significant figures than you had to start with. Couldn't put C for the same reason. Well, that plus decimals going the wrong direction. So it could be B or E would be valid answers. Now, I'm pretty sure I don't have one like that in the exam, but if one like that showed up, you could put E and argue your case and win, right? Based upon what I've told you so far. Okay? So don't be afraid to argue for points. All righty. Let's see. Taking too much time, I think. Oh, 23. Getting that one yet. We generally report a measurement by recording all of the certain digits plus how many uncertain digits. For instance, if you had a number like this, how many of those are certain? That's certain. That one's uncertain. The last one to the right is the uncertain one. So by convention, it's always one uncertain digit in the number. B. Okay. 24. No, we're ever going to get out of chapter 1. Let's see, 24. You're asked to determine the perimeter of a cover of your textbook. You measure the length at 39.36 centimeters and the width at 24.83 centimeters. How many significant figures should you report for this perimeter? Okay. The cover of your textbook. Sometimes it helps to draw a picture. So it's a length of 39.36 centimeters. Okay. And a width of 24.83. Okay. And we're asked for the perimeter. So how do we determine the perimeter? That plus that plus that plus that, right? Because you got two of these here, two of those there. And so we need to add those four together. Right? And the question refers to significant figures. Right? So we have a add subtract rule here. We line up the decimal points, and then we add things together, and then we round if necessary. So that's 12 plus, let's see, 3 times 6 is 18. And then 1 is 4, let's see, 6, 7. 7 and 16 is 23, isn't it? So that's 18, 19, 28. 2, 4, 6, and 6 is 12. Okay? So these all have the same number of decimal points, so we can keep everything, can't we? Now, what was the question? How many significant figures are in the answer? Yeah, 5. Right. We start with 4, 4, 4, 4, and end up with 5. Okay. The temptation is to say that times that times that times that. We have 4 in the answer, and that's wrong. Because it's not a multiply divide operation, it's add subtract. Different rules. $25, yes, 25. Okay. Consider the numbers 23.68 and 4.12. 4.12. The sum of these numbers has how many significant figures in the product? Okay. So the sum 10, 7, 8, 7, 2. The sum has 4 significant figures, right? How many will the product have? 3, right? So the answer is 4 and 3, which is D. Oh, this is one. No, that's not the right one. In my other class, I do the same. They get the same spiel as you do. Somebody asked me about a complex calculation where you have both sets of rules to deal with. And it's like this one, but the one they used is further down. So when I get to it, I'll stop and make a point. Using the rules of significant figures, calculate the following. 27. Let's see, 4.0021 minus 0.179. Okay. So nothing from that was that one. That's 3. 7 from 9 is 2. 1 from 9 is 8 and 3. Okay. So we've got the number of allowable decimals is here. So we have to round off to that position. 3.823 because 1's less than 5. That's why A is the answer. There it is, 32. Do these mixed calculations give you any trouble? Or do you feel sometimes? Okay, let's look at this one. 3.478 times 1.164 divided by 2.00, and that's milliliters. These are grams up here. And then minus 0.169, is it? Grams per milliliter. Okay. So what's the order of operation? PEMDAS, parentheses first. Right. So we do this operation first. Parentheses, exponent, there's no exponents. Multiply, divide. So we would do this one first, then we would do that one, and then add, subtract would be this one. So what do we have here? Yeah, I better get my calculator. 3.478. 8. Oops. There we go. Times 1.164. Okay, I get a number, 4.048392. Lots of decimals. Remember, when you're going to do a series of multiply divides, keep all your decimals until you get to the end. Right? We can't keep them across that operator because it's a different set of rules. But we can keep all of them for this one and round at the end. That eliminates rounding error. That doesn't eliminate it. It reduces the threat of rounding error. So I've got this big number here, and I'm going to divide by 2, 2.00. Okay. Now, out of this operation, I get 2.024196 grams per milliliter. Right? Grams up here, milliliters down there, just like this one. Now, how many of these can I keep? This is all multiply, divide. Just 3, right? And keep those 3, because that's 4, and that's 4, and this is 3. So I have to chop it off there. 2.02 grams per milliliter minus this one, 0.169. Right. 9 from 10 is 1, and 6 from 11 is 5, and 1 from 9 is 8. Left over is 1. 1.851. But the rule says we're limited to that one. So I have to round it to 185. Okay?
Why did you cut it off at 2.02?
Oh, because this is tenths, hundredths. This is tenths, hundredths, thousandths. There's no thousandths in this number.
I mean, when you had the big number on the left over there.
Oh, because there are 3 significant figures here. 4 there, 3 here. Because this is under the set of rules for multiply, divide. This is under the set of rules. Once we get that number, then we can do this one. Add, subtract is a different rule. Okay. So when you have compound operations like that, you've got to watch out where your operators are and what they mean. If we had a subtract or an add in here, it's in the parentheses, got to do it first. So whatever number comes out of that one, significant figures, then it goes into divide. And then we can do sometimes you have to round before you do the next operation if they're different rules. But if they're the same rule here as here, you can keep them all together and round at the end. Okay, is that the confusion? Okay. And the only purpose for that is just to eliminate rounding error. Okay. Let's see, 35. Got to write the number up on the last one. 35. Express the volume 781.2 cubic centimeters. 781.2 cubic centimeters in liters. Okay. It looks bad, but it's not. Remember this one equivalence. Cubic centimeter is exactly the same as a milliliter. Okay. In the hospitals, you'll see cc's. They say, give them so many cc's. It's milliliters. So we can substitute milliliters in there. They're exactly the same. So now we can use either the dimensional analysis route, or we can say, all right, that prefix, what does that prefix mean? That prefix means 10 to the minus 3. Right? So now that it's gone, it's this times 10 to the minus 3 liters. Oh, but does it want it reduced to, no, it wants standard notation. Okay, standard notation, 781.2. So now we're going to move the decimal which direction? Yeah, right. This has to get smaller as we put that information back into the number. So it goes 1, 2, 3. So we have 0.7812 liters. Okay. Let's see, 35, 37. Okay. We've got a combination unit conversion here. The pressure of the Earth's atmosphere at sea level is 14.7 pounds per square inch. That's taken as average. That's 1 atmosphere at sea level, 14.7. Actually, it's 14.69, but we'll leave it where they say. 37. 14.7 pounds per square inch. And they want us to convert it to grams per square meter. So we're headed for this one, grams per square meter. Okay. When you have multiple units of measure in a number that need to be converted, do them one at a time. So let's take pounds first. This is going to be a chained conversion. So we need to get rid of pounds. And what conversion factor are we given? Pounds and kilograms is what we're given. Right? Pounds on the bottom, kilograms on the top. So it's 2.205 pounds per kilogram. Yeah. Well, that did get us into the metric system, but it's still not there. So now we need to convert kilograms to grams. Kilograms, grams. So how many grams in a kilogram? Okay. Okay, now we're good. We've got that unit there. And I'm going to need some more room, so I got to get rid of that. We're going for square meters next. We need to get rid of inches. And what's our conversion factor given? Centimeters. 2.54 centimeters per inch. What's the problem? Yeah, that's a problem. But there's a bigger problem. Yeah.
It needs split.
No, inches is here. Numerator, denominator. This one's not squared. That one's squared and this one's not. So it's a real easy fix. If that ratio is valid, then if we square the numerator and the denominator, we still got the same ratio, right? It's like math. If you have the equivalence, you do the same thing to both sides, you haven't changed it. So it's like the equivalence, only now it's in a ratio. So all we have to do is square it. And that takes care of square inches. We just have to remember to square this before we do the calculation. And I'm guilty of forgetting to do that sometimes. Okay, we got centimeters, but we got square centimeters. Now we need square meters. So we need centimeters and meters. So we have 100 centimeters in a meter, but we still need to square it, correct? Because that's squared now. We need to square this, square that, square that. Now we've got square meters. Okay? That's the thinking part. The rest is just number crunching. So, and this is dimensional analysis. If you know that the units are correct through each operation, then the hard part's done. All you need to do now is calculate. Okay, so we need 14.7 divided by 2.205 times 1,000 divided by 2.54 squared. And times 10 squared. So what's 10 squared? 10 to the fourth. So that's 10,000. There we go. Times. Okay. I get 1.033331234 times 10 to the 7th grams per square meter. How many of those can we keep? These are all conversion factors, right? They're exact numbers. They have no bearing on the outcome. They're infinite significant figures. The only one that matters is that one. So we want to round to that position. 1.03 times 10 to the 7th. Okay? That was a chained conversion. And B is the answer. All righty. And you probably won't become comfortable with this type of operation unless you do a lot of it. And take a wrong turn and run up a dead end and have to come back and start over again. It happens. The density of liquid mercury is 13.6 grams per milliliter. What's its density in units of pounds per cubic inch? Okay, this is another example of chained conversion. And you just change the grams to pound first with your units, and then change milliliters to cubic inches. Should we do that one? What do you think? 41. Okay, 13.6 grams per milliliter. Grams per milliliter is the density of mercury. By the way, will that sink or float in water? Sink. If the density is greater than water, it'll sink. And what's the density of water? 1. 1 gram per milliliter. Okay. Let's see. We want to change that to pounds per cubic inch. Okay. All right. So if we do grams first, we want, and what do we have to work with? The same, pounds per kilogram, 2.205 pounds per kilogram. So we're going to need this in kilograms first. So 10 to the 3rd grams per kilogram, right? Here we go. Now we can change kilograms to pounds, 2.205 pounds per kilogram. There we go. Okay, that unit's done. We got pounds. Now we want to change milliliters. All right. Our relationship is centimeters to inches. Right? 2.54 centimeters is 1 inch. So how do we get milliliters out of that? Why do we change the milliliters? We use that identity. 1 milliliter is the same as 1 cubic centimeter. So you can put it in here just to keep things straight, like that. So that gets rid of the milliliters. Now we got cubic centimeters. All right, so we're going to get rid of centimeters and make cubic inches. And the relationship is 2.54 centimeters per inch, but we need cubed, right? We need this cubed here, and we need that cubed. So we're done. Now all we have to do is crunch the numbers. Okay. Like I say, don't forget to cube that when you're doing your calculations. All right. So the answer should come out as B, 4.91 times 10 to the minus 1 pounds per square cubic inch. Let's see, what do we have here? Ooh, a physics experiment. Yeah. Physics, 46. During the physics experiment, an electron is accelerated to 93% of the speed of light. What's the speed of the electron in miles per hour? All right. So if we're going to make it in miles per hour, and we're given the speed of light in meters per second, it's going to be a dual unit conversion for both meters and seconds. But we can't start with 3 times 10 to the 8th meters per second because we're only 93% of that. So what we have to do is change that 0.93 times 3 times 10 to the, let's say 8. Yeah, 8 meters per second. Okay, so this is what we're changing right here. This determines the number of significant figures because this multiplier has infinite significant figures. So we change miles per hour. Okay, so we need, what are we given? Kilometers is 0.6214 miles. 0.6124 miles. And kilometers. Oops. So what if we do this one in our head? How many meters in a kilometer? Right? So we actually skipped a step. We did this one in our head. Instead of changing meters to kilometers and then doing the kilometer thing. We know that 1 kilometer is 10 to the 3rd meters. So meters is gone. Now we need to change seconds to hours. Hours on the bottom, seconds on the top because denominator, numerator. How many seconds in an hour? Or do we need to do it? We can do it stepwise. How many seconds in a minute? Okay, minute. 60 seconds. And that gets rid of seconds. And then we know now that minutes, hour, is also 60, right? So that gets rid of minutes. So if we knew in advance, we could have said 3,600 seconds per hour. Right? But we got it set up. All we have to do is crunch the numbers. And it should come out as 6.2 times 10 to the 8th miles per hour, which is E.
What do you have to do whenever you add it all up? Like what is the step you go to calculate that?
Calculate what?
The final number.
Oh, to do that calculation? Oh, you just say, with my calculator, I put in all the numerator multipliers and then I divide by each one of the denominators. So I say 0.93 times this number, times that number, times that number, times that number. And then the result of that, I say divided by this number, by that number, by that number.
So you say 10 to the 3rd, or what do you put?
1,000. It's easier to put 1,000 in. Right. My calculator is set up to spit out answers in scientific notation, but it's easier. I mean, unless the input is in scientific notation, if it's simple like that, I just put it in standard notation. And that's the beauty of reverse Polish notation. I can do all that, no parentheses required. I think algebraic calculators, it probably does intermediate calculations for you. You say this times that, it spits out a number, and then you have to say times that, it spits out a number, so forth and so on.
So do you like add like all the bottom together and then divide it, or do you just say like divide by 1,000, divide by 1, divide by?
Yeah. There's no addition in here. It's all multiply, divide. If there were others over here, like 10 to the 2nd and 10 to the 1st, I would say 10 to the 3rd divided into it, 10 to the 2nd divided into it, 10 to the 1st divided into it. Or you could say 10 to the 3rd times 10 to the 2nd times 10 to the 1st and then divide that in. Doesn't matter. Still, you end up in the same place. But you may want to develop the skill of estimating. So what is this value going to be close to? It's still going to be close to 3. And 3 times 0.6 is what? It's about 1.6 or 7. So let's say 1.7. And then times 36. 1.7 times 36 is maybe 42 or 3. Right? And this would be 10 to the 5th. That's not right. 42 times 100. 4,200 times 10 to the 5th. So you take 3 of those decimals and put it back, you're back at 10 to the 8th. And it's about 4.2 times 10 to the. Yeah, I was in the ballpark. Answer 6.2 times 10 to the 8th. But when you're estimating, sometimes all you have to do is be sure that your the magnitude of your 10 power is in the right range. And that's what I just did. Doing that estimation in your head. And that takes practice. Okay. We're doing on time. We got till 3 o'clock, right? Before we have to do lab. Yep. Okay. I better get moving along so we can get into chapter 2. How about this one? This one looks bad, but it's not. That's another thing that word problems do. Besides trying to confuse the reader, they'll try to scare you too. By blowing a lot of blue smoke in your face. This 49. Right? In 1928, who cares, right? Who cares about the year? 29.3 grams of a new element was isolated from 660 kilograms of ore. There's the useful information. How much of the element was isolated from how much of the ore? Because the question is, what's the percent composition? 29.3 grams of the element per how much? 660 kilograms. And he wants to know what's the percent composition by mass. Well, you can't do apples and oranges, but as I say, right? That's grams, that's kilograms. So this has to be changed to grams, or that has to be changed to kilograms, either way. The easiest way, I think, is kilograms. Change the kilograms to grams. So you got what, 1,000 times there? 660 times 10 to the 3rd grams. Divided into 29.3 grams times 100. That's your percent. Okay? That looks simple enough. We can do that one. And divide it by 660, and then give you an exponent of 3, 5, and 100 times that. So I get, well, in scientific notation, it's 4.4. Wait a minute. That's only 2 significant figures, isn't it? Did I write that right? Yep. That's only 2 significant figures. So 4.439 means 3 is less than 5. So 4.4 times 10 to the minus 3%. Or it's probably in standard notation, isn't it? Yeah. So we need to move it 3 to the left. 1, 2, 3. Right here. So it's 0.0044%. D. Okay? Are we getting close? Kelvin. Temperature. So our starting point is 409 Kelvin. And what are our options? Degrees Fahrenheit, degrees Celsius. Right, you have to go Celsius first. So why don't we do that and see if either one of those Celsius matches? If it does, we're done. So Kelvin is equal to Celsius plus 273, correct? So that means Celsius would be this one minus 273. 631 degrees Celsius. Is that one of our answers? Yep, D. So we're done. It took what, less than a minute? 51. The melting point of a certain element is 391 degrees Celsius. 391 Celsius. What is this on the Fahrenheit scale? Okay. There is a page of useful information in the back. And it does have the formula for converting Fahrenheit, Celsius and Fahrenheit. But I just memorized this one. Fahrenheit is equal to 9/5. Excuse me. 9/5 or 1.8 times C plus 32. So we do have C, so we need 9/5 times 391 plus 32. And this is an exact number. So we're really only, when we add this to that calculation, this doesn't limit the number of decimals. Let's see, 391, enter 9 times 5 by, which is, let's see, 704. 704 plus 32, which is 736 degrees Fahrenheit. D. Okay. And like I always say, with a multiple choice type of test, pick the best answer. Sometimes it may not be exactly what you got. If you don't have the option to say none of the above, then you can argue your point like it wasn't exactly what I calculated. If that's not an option, then pick the best answer. All righty. 1984. Who cares? Some drums of uranium hexafluoride were lost in the English Channel, which is known for its cold water, 17 degrees Celsius. The melting point of uranium hexafluoride is 148 degrees Fahrenheit. In what physical state is the uranium hexafluoride in these drums? Okay, so the salient points here are, you don't have to know the formula for uranium hexafluoride. Let's see, this is 54. But if you're interested, uranium hexafluoride, hexa 6. So that's uranium hexafluoride. And what are we actually getting at here? It says the melting point is 148 degrees Fahrenheit. But the temperature, once the temperature inside the drum equilibrates with the water outside, the temperature inside is going to be 17 degrees Celsius. Okay? So if this is the melting point, When is it solid and when is it liquid? If it's below that temperature, it's solid. Right? If it's above that temperature, it's liquid. But we can't compare these two like that. So we've got to change. We either got to change this one into Fahrenheit or this one into Celsius. We've already done one into Fahrenheit, so let's do the Fahrenheit into Celsius. And that, again, is this formula. And if we plug Fahrenheit in here, 148 equals, well, why don't we just make it quicker? We know we're going to have to subtract this from both sides, right? 32 equals 9/5 C, correct? Okay, so now we have to do is take this number and say 5/9 times that number, and that'll give us our answer. $148, and we really don't have to be concerned with significant figures, probably, especially if the results of this are way far away from that number. Then it'd be easy to determine regardless of the significant figures. 148 and 32 subtracted from that, 5 times 95. So I get 64. So the melting point of uranium hexafluoride is 64 degrees. Is it colder or warmer than that? It's colder. So this is going to be solid. Okay? And that's A, should be the answer to that. Let's see here. Ooh, this one gave one of my students trouble trying to explain this one. So maybe we better do it. 56. Word problems have a tendency to do that. A monolayer. What's a monolayer? One layer, exactly right. It's composed of oleic acid, a fatty acid. That's a monolayer. And if it's sitting on top of water, which this is, it orients itself so that, and fatty acids have a hydrophobic end and a hydrophilic end. So the hydrophilic end is going to be oriented toward the water, and the hydrophobic end is going to be away from the water. So that's why this monolayer of oleic acid is a single layer of oleic acid molecules in a cylinder, right? And the height of the cylinder is the length of the molecule. Okay, and they state that in the problem. What's the thickness of the monolayer? All right, so what we need to do is say, okay, here we got this monolayer, like that, sitting on top of the water. And let's see, it's really a cylinder. This is the height of the cylinder, right? If you turn it kind of like this. And this is the diameter of the cylinder. Diameter. So, what's the volume of that cylinder? I had geometry. Are they used in geometry, or is this, yeah, I think it's geometry. The volume of that cylinder is equal to, actually the area, actually, right, let me look at the information they gave us. Oh, they've already given us the area. All right, so we don't need that. So the area is equal to 20.0 square centimeters. All right, so the volume is going to be the area times the height. Okay? We know what the area is. We're actually searching for the height. So what else do we need? We have the area. We need the volume. What's the volume of that cylinder? Well, we get that information from the density. Remember, density equals mass per unit volume. And we're given the density here as 0.895 grams per milliliter. 0.895 grams per milliliter equals, and we're given the mass of the oleic acid, 3.26 times 10 to the minus 6 grams. There's volume. Okay, so now we can solve for the volume. And then the volume can go here. We know that. We can solve for that. Okay. All right, so what's the volume? Well, if we bring the volume over here and the density over here, we just divide the density into the mass. And that gives us volume in milliliters. 3.26 exponent minus 6. And then 0.895 divided. And that's 3.64. 3 significant figures. I'm going to round off before I even put it up here. Times 10 to the minus 6 milliliters. Okay. Well, let's see. What units is this going to be in? This is in cubic centimeters. If that's in centimeters, this is going to be volume in cubic centimeters. Right? But that's not a problem, is it? Because they're exactly the same. So now we put this value in volume. 0.64 times 10 to the minus 6 cubic centimeters is equal to the area, square centimeters, times the height. So now to get the height, we just divide this number by that number. 3 significant figures also. And I get, let's see, 1.82 times 10 to the minus 7 centimeters. Now, is that the right units? If we divide centimeters squared into centimeters cubed, that leaves us with centimeters, doesn't it? Because it's the numerator exponent minus the denominator exponent. 3 minus 2 is centimeters. So we're good there. Let's see, is that one of the answers? Close, 1.80. So pick the best answer. And I could have made a mistake in my calculations too. Let's see, that was 56. Is this going too fast? Okay. The density of gasoline is 0.7025. Yeah. The density of gasoline is 0.7025 grams per milliliter. When gasoline is added to water, what will it do? This is kind of a difficult question because we haven't talked about solutions yet. Will the gasoline mix in water? The answer is no. Because water is polar and gasoline is nonpolar. And see, we haven't talked about that yet. So that wouldn't be a good question for this test, simply because we haven't covered the material. But if I give you that information, you know it's not going to mix, then will it float or sink? Right, because that density is less than 1. So that's why when you have a tanker on the ocean that springs a leak and it's carrying refined gasoline, you see a slick across the surface of the water. And the only way it mixes in is with wave action. And that's possible. See, it's a complex procedure that the spill undergoes. And the only way it sinks is if it mixes with suspended soil particles. If it does that, then it'll sink to the bottom and contaminate whatever life forms on the bottom. Anyway, that's 57. See, do we need to do 58? Piece of zinc with a mass? Yes. Okay. The purpose of this one is to help you with one of our upcoming labs. 58. Might even be next week. No. Yeah. Today, we're supposed to do graphing techniques. But we don't have a lab next week because we have an exam. And then more material. Okay. So I won't give you this lab until next week, probably. Lab techniques. Next week we'll have a lab, and then we'll cover new material right after. Not have a lab. Okay, 58. A piece of zinc with a mass of 12.14 grams. So we got zinc, and its mass is 12.14 grams. Is submerged in water that's 46.3 cubic centimeters. So it's probably a graduated cylinder. And the water to start with is 46.3 cubic centimeters, which is the same as milliliters. And then after the submergence, the water level is now 48.0. Now it's 48.0 cubic centimeters after we put the chunk of zinc in the bottom. Okay? So the question is, what's the density, right? What's the density of zinc? Well, what do we need to know for density? Mass per unit volume, right? Okay, we got the mass, no problem. What's the volume of that zinc? Why did the water go from 46.3 to 48? Because that chunk of zinc displaced some water, right? So the volume of the zinc is the difference between these two. 48 minus 46.3. So all we have to do is say this, grams, and then 48 minus 46.3 cubic centimeters. And these both have, well, we're going to have to do that subtraction. 7 and 1.7, right? So 1.7 here divided into that, which means we only have two significant figures, correct? 1.7 into 12.14, and that's 7.1, rounded off, grams per cubic centimeter. B. B is the answer. So if you're going to measure the volume of an irregular object, submergence in water would work, except what? If your object reacts with water, that would be a no-no. Like, you couldn't measure the volume of an irregular chunk of sodium. You put sodium in water and it reacts. It produces sodium hydroxide and hydrogen gas. And all you need is a spark and you got an explosion. So if we were to do that, say, with sodium, what would we use? Something that wouldn't react with sodium, like oil, mineral oil is good. In fact, that's how you store it. Sodium is stored under mineral oil so that it won't react with atmospheric moisture or oxygen for that matter. Okay, 58. We're going to run over a little bit, I think. The boiling of water is what kind of change? Right? It's either A or B. It's a physical change, right? Boiling water. But why? Because the water merely disappears? It could disappear with a chemical reaction too, couldn't it? So because the gaseous water is chemically the same as the liquid. Yep, that gets it. Let's see. Oh, this is a good one. You see these representations of elements and compounds. Okay, it's hard to tell, but I'll point it out to you. A has a mixture of two different elements because they're single circles, but one of them is shaded and the other one's open. Right? So, and the distance between them indicates what? It's a gas, right? So you got a mixture of elements in a gas. B is a regular arrangement of a single shaded circle. So that's a pure element in a regular arrangement, which makes it a solid. That's a solid. C is a combination of a shaded circle and a big open circle. And these individual particles are acting like separate units, which makes them molecules. So this is a compound, and they're spread out far apart, which makes them a gas. It's a gaseous compound. Okay? How about D? It looks like D has two different types. It's got a shaded and a open circle, but they're not combined, right? And they're irregularly arranged. And it looks, if we look at them close, they're not homogeneous either, right? We got concentrations of some dark ones here and then light ones over here. So that's a heterogeneous mixture of two elements. And how about this one? Well, first of all, you have compounds and elements, right? The square is an element, and these are compounds. But it looks like they're arranged regularly, like there, they're opposite, and then switch again, switch again, switch again. They're homogeneous mixtures of an element and a compound. Now, I'm not sure whether it's a liquid. Doesn't look like it's far enough apart to be a gas, but they're regularly arranged. So it could be a solution of some kind. But look at the questions now that you have an idea of what they are. Which best represents a homogeneous mixture of an element and a compound? It was that last one, right? Element and a compound, and they're homogeneous. So E's for 70. Which best represents a gaseous compound? A gaseous compound, right there, C. That's a compound, and they're far enough apart to be a gas. 72. Which best represents a solid element? Right? You need an element, and then it has to be solid. So actually, the only one that's an element is B. Right? It's pure. So that was easy. And then D, which represents a heterogeneous mixture of two elements? I think that's D. You got two separate elements, and they're heterogeneous. Okay. Sometimes that one throws students because it's, right, what do you mean with all those circles and squares and shades and not shades? 75. Which of the following has a different value on the moon compared to Earth? Yeah, weight. Time's not going to change. Well, we haven't talked about moles yet, but moles is just numbers of stuff. So that wouldn't change. Yeah, mass doesn't change either. It's just weight. Weight is what is the mass response to a gravitational field. Which separation technique, number 80, which separation technique is based on difference in the volatility of a substance to be separated? Okay. What do we mean by volatility? How easily does the liquid become a vapor? Or if it's more volatile, probably has a lower boiling point. Less volatile, higher boiling point. And you can make use of those physical differences between the substances to separate them by distillation. Right? Every moonshiner knows how to do that. Water boils at 100 degrees Celsius. Ethanol boils at about 70 degrees Celsius. So you can heat it up and little or no water is going to come off until all the ethanol is gone. So you can bring the ethanol over. Some water will come with it. And it will, and then you condense it. Once you get it into the vapor, then you condense it and stick it in your mason jars and sell it, or you dilute it. You may not want to give pure grain alcohol to your customers. What about the others? Filtration. What is that separation based upon? I'm sorry? Filtration. You can have a solid in a liquid and separate them, but they're based upon particle size because the filter medium has pores in it. And if the pores are very, very, very small, then you can retain much, much smaller particles. If they're very big, then you can only retain large particles. That's filtration. Solvent extraction. We haven't talked about that much. Solvent extraction makes use of solubility. So if you've got a mixture of things and they're differentially soluble in a medium of some sort, then you can mix them together. One of them may go into solution and the other one won't. So the solvent will extract something like, I think we have an experiment where we separate sand and table salt. Right? Sand won't dissolve in water, but the salt will. So we mix them both in water. The solvent extracts the sodium chloride into solution. You separate it. You take the leftover, which is the sand, you dry it and weigh it, and then you take the solution with the salt and you evaporate the water, and now you have a solid salt. You got those two masses, and you can tell what's their percentage composition. So solvent extraction, that's one example. Solvent extraction, you can separate two liquids also. I did that for my master's. But it was a pretty involved process, and you have to get the mixture of your solvents exactly right to make the separation. Anyway, paper chromatography. Paper chromatography is rather old, like it was invented in the 1800s, I think. What you have is a sheet of paper, and then you have a solvent down here, and you have an enclosed vessel. So you put your sample, usually an extract of something. It's a mixture. So you spot it on the paper first, like that maybe. And then as the solvent is sucked up into the paper, it moves, and the components of your mixtures are differentially absorbed onto the paper and dissolved in the moving solvent. So it's a differential of how they behave against the paper versus the solvent. If they're really strongly attracted to the paper, then they'll stay on the paper more than they will the solvent, and they won't move much. But if they really like the solvent and not the paper so much, they'll stay in the solvent more, and they'll move higher up. So it's a differential attraction between the media, the solid media, and what we call the mobile phase. Okay. That's how we base paper chromatography. Actually, that's the basic idea for all chromatographies. Paper was the first. Then they went to a thin layer. They took a layer of silicon dioxide, usually, sometimes it's coated with something, and they layer it on a glass plate, let it dry, and then they use that instead of the paper. Or you can have a tube packed with little beads of a certain type of absorbent, and you can, under high pressure, drive the solvent and your sample through it, and they will differentially be attracted to the beads or the solvent, and the ones that are more strongly attracted to the stationary phase will be the last ones to come out. And the pressures behind high pressure liquid chromatography, they can be at 30, 40, 50 atmospheres. I mean, really high pressure. So the stationary phase is in the stainless steel tubes. It needs to stand up to that pressure. Okay. Finally, and we got 15 minutes left. Chapter 2. All right, let's see. We should be able to get through these pretty quick, these first ones. The first people to attempt to explain why chemical changes occur. The ancient Greeks. They tried to explain it. They came up with the concept of the atom. The first chemist to perform truly quantitative experiments was Robert Boyle. He started with gases, making measurements for gases. The scientist who discovered the law of conservation of mass and is also called the father of modern chemistry. He was the one that lost his head in the French Revolution. So if you know he's French, look down there and see which one looks French. Yeah, Proust looks a little French, but he's not the right one. Lavoisier. He was the Frenchman who came up with the law of conservation of mass. He was also a tax collector, so when the French Revolution rolled around, he lost his head. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? So to answer this one, you need two compounds. You need two elements. Two elements in the compound, and they have to be in different proportions. So look at what we've got here. We've got A is ammonium and ammonium chloride. Right? So you don't have two there. Ammonium would be a separate unit because it's a polyatomic ion, and chloride would be a separate unit. So you need chloride in the other one. And you're not going to get that anyway. Zinc oxide and zinc chloride. Right? Well, you have two elements in each one, but they're not the same two. So that won't work. How about water and hydrogen chloride? Nope. You got hydrogen in both of them, but you got oxygen in one and chloride in the other. That won't work because the law of multiple proportions references ratios of one of the elements to the first element. How about NO and NO2? Ha, there you go. You got two of the same elements in different compounds, and they're in different ratios. So if we hold nitrogen constant, then the oxygen changes by whole numbers. Right? A certain mass of oxygen in NO, and in NO2, the ratio makes it double. Okay? We don't even need to go to E because it's wrong. For the same reasons as the others. Okay. Oh, this is a good one. 7. It's a little brain teaser. Put on your thinking caps. 7. A sample of chemical X is found to contain, the sample of X is found to contain what? 5 grams of oxygen, 10 grams of carbon, and how much nitrogen? 20 grams of nitrogen. That's everything in the compound. So the question is, what if you have 70 grams of this X compound? If you have 70 grams of it, how many grams of carbon will you have? Well, the law of definite proportions says that once you've established the ratio of elements in a compound, that ratio is fixed. So if you have more of it, still got the same ratio. So how much do we have here actually? 35 grams? That's total. So what if we have now 70 grams? Well, wouldn't we have double this, double that, because this is double? Right, so we'd have 40 this here, we'd have 20 here, and we have 10 here. So carbon would be 20 grams. E should be the answer. Does that make sense? Okay. That's an illustration of the law of definite proportions. Seven, 9. Which of the following statements from Dalton's atomic theory is no longer true? Okay, so Dalton said that all matter was composed of a simple particle, the atom, just like the Greeks did. Only he said every element has its own unique atom. So the atom of gold is different than the atom of carbon. But he said within that pure element, all the atoms that are in there are identical. Okay, is that true? Well, A says elements are made up of tiny particles called atoms. Yeah, that's still true. B says atoms are not created or destroyed in chemical reactions. Yep, that's true. Because of the law of Lavoisier's law, conservation of mass. You can't destroy atoms in a chemical reaction. Otherwise, you wouldn't conserve your mass. How about C? All atoms of a given element are identical. No. We know about isotopes now. So they may be chemically very similar, but they're physically not. They're different because they have different numbers of neutrons. So C is false. C is the one we're looking for. Atoms are indivisible in chemical reactions. True. All these statements are true. Nope. No. So the answer is C. That's the one that Dalton got wrong. 11. The chemist credited for inventing a set of symbols for writing elements. I think I covered this one. He was a Swedish guy. Berzelius. He came up with the letter system that we use to identify each of the elements. 12, Avogadro's hypothesis states what? Well, remember, let's see, 12. Avogadro said if you have two gases and their volumes are equal and their pressures inside the container are equal, and what else? Their temperatures are equal, and the number of particles in each must also be equal. That's Avogadro's law. Well, they call it a hypothesis here, but it's pretty well established. And the one that answers that question is D. Okay, 13. The first scientist to show that atoms emit any negative particles was, who studied the electron first? That we know about. J.J. Thomson. He actually determined the ratio of mass to charge, or charge to mass, whichever way. He didn't figure out what the mass of the particle of the electron was, but he did the ratio of charge to mass. And later on, shoot, my mind's gone blank. Never mind. Many classic experiments, number 14, have given us indirect evidence of nature of the atom. Which of the experiments listed below did not give us the results it described? Okay, A, the Rutherford experiment, remember that one? Gold foil experiment. He was trying to disprove the plum pudding model and put forth the nuclear model for the atom. So Rutherford's experiment proved the Thomson plum pudding model of the atoms to be essentially correct. Nope, he disproved that model. Right? The plum pudding model says that the electrons and protons are just kind of in this big jelly mass spotted around. Rutherford said no. The protons are in the center, very dense nucleus, and the electrons are out here somewhere. And his experiment proved it. So with that, the plum pudding model was dead. So we found our answer. A. 15. The scientist whose alpha particle scattering experiment led him to conclude that, oh, well, that was Rutherford, right? 14 and 15 are kissing cousins. "16. Alpha particles beamed at thin metal foil may what?" Well, now we're still talking about Rutherford's experiment. What will they do? Well, they can pass through, right? If they don't encounter a nucleus, right? They're so heavy, electrons don't stand in the way. Or they can be deflected by a glancing blow, or they can be sent essentially straight back at the source if they hit head on to a nucleus. So that would be E. A, B, and C are all right. Any one of those things could happen. 17, which of the following statements about atomic structure is false? All right, an atom is mostly empty space. Is that true? Yeah, it's mostly empty space. The electrons out there are just, by comparison, they've got lots of room. Almost all of the mass of the atom is concentrated in the nucleus. Yep. The protons and neutrons in the nucleus are very tightly packed. Oh yeah, very tightly packed. So if a bunch of positive charges, dense positive charges are packed in the nucleus really close, how do you keep them from flying apart? It's called the strong nuclear force, one of the four fundamental forces of nature. And it's facilitated by the presence of neutrons. We didn't go into that kind of detail, but the more protons you have, the more neutrons you need to keep them together. So that's why when you first start off in the periodic table, hydrogen's got one proton and one electron. You know, unless it's an isotope. But as you get bigger, helium's got two protons, so it needs two neutrons to hold things together. And for a while, the most common isotopes are 1-to-1 proton-neutrons. But at some point, you have so much positive repulsion in the nucleus, you need many more neutrons to help stabilize it. So when you get to the heavier elements, you get larger and larger and larger numbers of neutrons as opposed to the protons. Okay. Which one is false? The number of protons and neutrons is always the same in the neutral atom. Not always. We know about isotopes and we know about heavy elements. So D is false. Which of the following atomic symbols is incorrect? 20. So how do we deal with that? Well, we got the symbols, right? And we got a periodic table. So you just look up the atomic number, the Z number in the lower left hand, and see if they match first, right? See if there are anything wrong there, and you can find out, maybe you can figure out which one's incorrect that way. Because if you find it that way, you don't have to go any further, right? Does carbon have 6 protons? Yep. How about chlorine? Does it have 17? Yep. How about phosphorus? Does it have 15? Yep. How about potassium? Does it have 19? Over there on the left. K. Yeah, that's potassium. No. P is phosphorus. K is potassium. Yeah, 19. So that one's good. How about nitrogen? This says 8. That says 7. Okay, we found our one. E is wrong. Okay, how about the element rhenium, Re, which is not one that I want you to memorize, right? But you can look it up in the table. Rhenium is, let's see, where is it? I had it located a while ago. Well, oh, there it is, 75. Atomic number 75. It's a transition element. Has 2 stable isotopes and 18 unstable isotopes. Rhenium, that doesn't matter. Rhenium 185 has in its nucleus, if it's 75, and they're giving us an isotope with 185 is the mass number, then it has 75 protons. And how many neutrons? 110, yep. So 75 and 110 is D. Okay. Which among the following represent a set of isotopes? Right? What do we need for isotopes? We need the same number of protons and different numbers of neutrons. So which ones of these, Roman numeral 1 through 5, which ones match that? Which would be isotopes? The first one is 20 protons. We got any more with 20? Yeah, Roman numeral 1 and Roman numeral 4. So these are isotopes, right? 21, 2 and 5. They've got the same number of protons and different neutrons. 2 and 5. And then 3 doesn't have a match. So throw 3 out. So 1 and 4 and 2 and 5. 1 and 4. Definition of an isotope. 2 different atoms with the same number of protons, means it's the same element, and different numbers of neutrons. Okay, we covered that, didn't we? Okay. Roman numeral 3 doesn't have a match. So D, 1 and 4 and 2 and 5 would answer that question. A species with 12 protons and 10 electrons. So we got to find out what's the element first, and then what's the charge. 12 protons and 10 electrons. So what's the charge going to be? Right. Now we can figure out what that symbol is by 12. So what's 12? It's like magnesium, doesn't it? Yeah, magnesium. So magnesium 2 plus would answer that, which would be C. Okay. Oh, 29. The number of protons, neutrons, and electrons in that particular ion. 1939. Yeah. K plus. Okay, so how many protons? 19. That means it's got to be C, D, or E. Can't be A or B. How about the number of neutrons? 20. So, well, it still could be C, D, or E. How many electrons? Because it's an ion, right? So how do you get a positive charge if you've got 19 protons and you need one excess proton? 18 electrons, yep. So that makes it E. Okay? Do a little detective work here. Let's see here. Which of the following are incorrectly paired? You know what? Since we're so short on time, these are matching symbols with either the names of the elements or where they're located. Okay, we can skip 34, 35, and 36 because they're just a matter of memorizing the symbols. But we may want to take a look at 33 because this refers to groupings in the periodic table. So is strontium an alkaline earth? So you look at your periodic table, where is strontium? Left side, second column over, right? Is that an alkaline earth? The first column, the first group is alkali metals. The second one is alkaline earths. So that's true. Strontium is an alkaline earth. How about Ta? I didn't have you memorize that one, did I? Ta, that's tantalum. So you just have to find the symbol. Where is it? Right. It's in the, actually in the 6th period. If you look at the numbers down the left-hand side, tantalum in the 6th period. So what region is it in? That area in there. That's the transition metals. And that's what it says. It's a transition metal. How about F? Fluorine? Where is it located? That group has a name. Right? It's the second one over from the right. And that group is the halogens. And that's true. It's a halogen. How about H? Is H a noble gas? Nope. Now its neighbor, helium, is a noble gas, but not hydrogen. So that's the incorrect one. And Ru is ruthenium. It is also a transition metal, and you can find it in the middle of just below iron, Fe. So it's a transition metal also. The bad one is hydrogen. It's not a noble gas. 37. All of the following are characteristics of metal except what? So are metals good conductors of heat? Oh yeah. How about malleable? Can you bend them? Can you shape them? Yep. Are they ductile? That means can you stretch them into a thin wire? Yeah. Are they often lustrous? If they're polished, they are. E, tend to gain electrons in chemical reactions. No, metals tend to lose electrons. So E is the answer there. Let's see. Oh, this is a good one. 41. Another detective story. Okay, 41. You're given a compound with the formula MCl2. MCl2. And M stands for metal. There are no M's up there. Well, they tell you it's a metal. You're told that the metal ion has 26 electrons. 26 electrons in that compound. What's the identity of the metal? Okay. So if it has 26 electrons, what is the charge on the metal? Do we know what the charge on chlorine is? Yeah, it's a halogen. So it's a -1 charge. So that means 2 times -1 is -2. That have to be balanced by a 2+ over here. Okay? Because it's a neutral compound. Now, how did that metal get a 2+ charge? Electrons. It lost 2 electrons. So now it has 2 more than that as protons, correct? Yeah, I think that's what you were trying to say. Yeah. 28 protons. Now we know the number of protons. Go straight to the periodic table. 28, 28. Nickel. So this nickel there is the compound. And does that answer the question? Yeah, E, nickel. That's the element that formed the ion in the compound. How many oxygen atoms are in the formula of that compound? 45. Calcium phosphate, right? I think that's right. Phosphate is a polyatomic ion with a 3- charge. Calcium is an alkaline earth with a 2+ charge. So we just take the 3 charge and put it over here, and the 2 charge and put it over here. 3 times 2+ is 6+. 2 times 3- is 6-. It's balanced. I was just checking to see if they were right. But the question is, how many oxygen atoms are in that formula unit? Well, you got 4 here, right? But you've also got 2 of those polyatomics. So you have 8 oxygens. My dogs are barking. I've been on my feet all day. Okay. Let me see. Do we need to name these? Yeah, I guess we do. 47, FeO. How would we name that? First of all, remember type 1, type 2, type 3 compounds? Okay, so let's see. This is 47. FeO. So is that a 1, 2, or a 3? Well, it's not a 3 because it's a metal nonmetal. Right? So it has to be a 1 or a 2. So what differentiates 1 from 2? The possibility of multiple charges. Does iron, can it have multiple charges? Well, where is it? It's a transition metal. Yeah, it can have multiple charges. So that means it's a type 2. So we have to name it according to the type 2 convention. So we're going to have iron, and then oxide. And then we say, what is the charge on the iron? Well, oxygen is always what? In these ionic compounds. It's a 2- charge. So that means this one iron has to be a 2 plus. That means
How do you know which charge it is?
which one?
Like all of them. Like whenever you look at them, how do you know just outright what the charge is?
On the oxygens?
Yeah.
With the periodic table, we know that in ionic compounds, these guys are always +1. Alkali metals are +1, +2, +3. These are always -1, -2. That's why I knew oxygen was -2, -3. These are kind of squared up, so you can't say that.
But the ones in the middle,
These
+2.
These are variable. These vary, except for silver is always +1, zinc is always +2, and I left this one out before. Cadmium is also always +2. So if you have a metal, non-metal compound with any of these, you can name it type 1 convention. You don't have to say what the charge is because it's always 1, 2, or 2. But the rest of them have multiple charges. Okay. And I knew that oxygen was a 2- charge because it's 2 to the left of the noble gases. Noble gases are 0 charge always. So fluorine is a -1 charge. Now all of its family are -1. Chalcogens, oxygen group, they're always -2. And the pnictogens, the nitrogen group, they're always -3 in ionic compounds. They have to be combined with a metal. If you combine them with each other, non-metal, non-metal, now you've got a type 3 compound, and there are no ions in there. So that's why we have to say exactly how many there are in the formula. But the type 1, type 2, you base it upon charge balance.
Like how did you know iron was +2?
Oh, because I know this one is -2. And we have to balance the charge. This is a neutral compound. So we have to balance those 2 minuses with a 2 plus. Now, there's only 1 iron here, so all of that 2 plus has to go on that 1 iron. That's why I can say this iron is 2 plus charge. If we had, for example, this one, like that, then this would be still -2, but the total charge here would be -6, right? That means this one has to be +6 total. I shouldn't put it there. That's a mistake. It has to be +6 total for that iron, but there are 2 of them. So each one would be +3. Then when you write this name for that one, it would be 3. So type 1s and type 2s are all charge balance. And you have to know what one of them is. Well, in the case of type 2s, you have to know what the non-metal is in order to tell what the metal is. Okay. All righty. 48, correct name of Ca2 plus. What's the correct name of this one? Well, we can't just say the element name, right? Because it's an ion. But we can say this. Say it's an ion. But do we need to say anything about the charge? Where did it come from? It came from alkaline earths, and they're always +2. So if we put a charge in here, that's just redundant because we know it's +2 always when it's an ion. So that's why calcium ion is all you need. It's unambiguous and not redundant. So that's why the answer to that one is C. Calcium ion says it all. Okay. What's the subscript of barium in the formula of barium sulfate? This is 51. I think I got a little room over here. 51. Barium sulfate. Okay. Barium, we know, would be an element. We just need to find it up there. Where is it? Second column, right? It's an alkaline metal, alkaline earth, excuse me. Right? So if it's in the second column, it has a 2+ charge. So just for budgeting purposes, I'm gonna put the charge there. But when you write it out, you don't have to put the charge. How about sulfate? What is it? It's not sulfide, right? Sulfide would be sulfur, just plain sulfur. Sulfate is a polyatomic ion. So that's where you go to your list of polyatomics, which will be on the exam. It'll be in the back, useful information. Here it is. You look up sulfate and you write what sulfate is, SO4. And what is its charge? 2-. So a 2+ balances a 2-. You only need one of each. You're done. So to answer the question, what's the subscript of barium? It's 1. There's an understood 1 there. We never write 1s, but it's there. The trick to that one is recognizing, actually 2 tricks. Recognizing that barium is a fixed charge of 2+, and sulfate is a polyatomic ion. Anytime something ends with an ATE, you can bet it's polyatomic. ATE is an archaic term that refers to oxygen. So it's sulfur and oxygen. Only you can have different combinations of sulfur and oxygen. You can have SO4 2-. You can have SO3 2-. SO4 is sulfate. SO3 2- is sulfite. So we have to change the ending a little bit to accommodate. Sodium dihydrogen phosphate. In this case, dihydrogen phosphate is the polyatomic ion. So we have sodium dihydrogen phosphate. And you look up your polyatomic, say, all right, what's the charge? Well, the charge is 1. And the charge on sodium is +1 because it's in the first group. Okay. So that's it. NaH2PO4. You're done. Okay, 56. Naming, looks like we're naming acids here with 56. I'm going to run us out of time, aren't I? Having trouble naming acids? What do you look for first? Hydrogen. Leading off with hydrogen. So do we have hydrogen? Yeah, every one of them's got hydrogen first. Okay, then you look for oxygen. If you don't have oxygen, you start the name with hydro. If you do have oxygen, you don't start the name with hydro. You look to the polyatomic that's part of that, and you say, what is that polyatomic ion called? So the first one, SO4, is sulfate. Don't start it with hydro. Say 8s become X. So sulfuric acid, that covers it. That one's good. CO3, what is that? So you look it up in your polyatomic, that's carbonate. So carbonate, 8s become X, it's carbonic acid. Right? That's what you drink in pop, carbonated beverages. Carbon dioxide dissolved in water reacts with water and forms carbonic acid. Okay, that's not the only thing in pop, but it's there. That one's true. PO4 is phosphate. H become X, phosphoric acid. Yep, that's good. How about HCN? Is that cyanic acid? Well, CN is the cyanide ion, right? But there's no oxygen. So you need to start it with hydro. So it's hydrocyanic acid. That one's false. And HCl is true. That's hydrochloric acid. No oxygen, start it with hydro. And chloride becomes ic, hydrochloric. Is that still giving anybody trouble? Sometimes naming acid does give students trouble, and some just eat it up. I'm going to let you do that one on your own. Since we're running out of time, let's do these fill in the blanks. All right, so what we've got here is 61. We got a table with 1, 2, 3, 4, 5. So we got here, got here, got here, like that. 1, 2, 3, 4, 5. There we go. We need 1, 2, 3, 4, 5 across. So if we do this, that. And we got the symbol here. We've got number of protons. We've got number of neutrons, number of electrons, and charge. Right there. Okay. What are we given? Well, we're given 206 PB. 206 PB. We're also given Mn 2 plus. And this one we're given 31 protons and 52 neutrons. And then we get 38, 75, 30. And we're given 54 here. And we're given 3 plus here and 2 plus here. Okay, and the rest are what we need to fill in. Okay, how about this one? Does it have a charge? Nope. No charge, because it's not given. No charge. How about the number of protons? Well, now you got to go look. Lead, Pb. 82 protons, right? 82 protons. How many electrons are there? Exactly the same, because there's no charge. Now, how many neutrons? Subtract 82 from 206, right? Yeah. Okay, so let's see, that's 4, and then 8 from 10 is 2, 124. Okay, so that one's done. How about this one? Do we know the symbol? 31 protons. Gallium, right? Gallium. Let's be consistent. Protons and neutrons will be 69, right? 69. But it has a charge. There we go. Now, how many electrons does it have? It's got a 3 plus charge and 31 protons, 28. Exactly right. How about this one? 52 protons. Same as the number of cards in a deck, right? Tellurium. Let's see. Protons and neutrons. Okay. And does it have a charge? Let's see. Protons and electrons. -2. Okay. There we go. And manganese, it doesn't say what the, so this one stands alone. You don't have to put the numbers in. But we do want to put this in, number of protons. So we look at manganese. Top row of the transition metals. 25? Yep, 25. And it's got a charge on it. So how many electrons are there? Yep. There you go. So now our table is full. Uh, 62 is kind of like the same thing, right? Protons, neutrons, electrons, atomic number, mass number, net charge. So we're not going to do that one. It's repetition. This is 63 is know your symbols. So silver's kind of funny. It's Ag, right? Argentum. Calcium is Ca, iodine's I. Copper is Cu, not Co. Cu for cuprum. What's Co? Uh-huh. And phosphorus is P. Write the names of the following compounds. So with FeSO4, that's 64. FeSO4, what we need to know is this one is a 2- charge because it's a polyatomic ion. So that means this one has to be a 2+ because there's only one of them. So now we can write the name, iron 2 sulfate. NaC2H3O2. If you see in a compound, it's got 3 or more elements and one of them is oxygen, suspect polyatomics. And in this case, you'd be right. C2H3O2 -1 is acetate ion. And it's combined with sodium +1 because it's an alkali metal. So sodium acetate, it's a type 1 naming convention. That's it, you're done. You don't have to say the charge because it comes from the first group. It's always +1. Potassium nitrite, NO2 is the nitrite ion. K is potassium. And it too is always +1 charge. So that's all you have to say. Calcium hydroxide, CaOH2. OH is a polyatomic ion with a -1 charge. Calcium is an alkaline earth with a 2+ charge. It comes from the second group. And that means you need 2 hydroxyls. So you can't split the hydroxyl up. It's a polyatomic. That's why you have parentheses. And you need 2 of them, right, to make 2- charge. To balance your 2+ from calcium. NiCO3. Carbonate's a polyatomic ion. Right? It has a 2- charge. So that means nickel has to be a 2+ charge because there's only one of them. So it's nickel 2 carbonate. And you know that because nickel comes from the transition metals. And it's not zinc, it's not silver, it's not cadmium. So it has possibility of multiple charges. Did I lose anybody? Need to work on it, huh? Okay, you got another week. Let's see what we got here. Oh, that's kind of messed up. Nitrate ion. In fact, that's wrong. I'm missing a subscript. Nitrate is this. Right? So that one's wrong. Unless there's a 3 that's in the wrong place up there out of the way. I don't know if that's true or not. Doesn't look like it is though. So that one's wrong. Aluminum oxide. Right? Aluminum and oxide. Type 1, type 2, type 3. Well, it's not type 3, it's a metal, non-metal. Does aluminum have a fixed charge? Yep, it's in that third group over under boron. So aluminum is always +3. And this one, oxygen is always -2. So put the 2 over here and the 3 over here. 6 minus, 6 plus. Good to go. Al2O3. Ammonium ion. That's a polyatomic ion. And really, you just look it up. Look in the chart. Ammonium NH4 plus 1. Perchloric acid. Okay, this one might be a little more difficult. So we know that it doesn't say something chloride. Ide becomes ic. So we would think maybe that, right? But that's already taken. That's hydrochloric acid. Perchloric, since it doesn't have hydro in the front of it, it's got to have oxygen in it. Right? So the oxygen comes in here. Now we need to look at where did that come from? Polyatomic ion. Look it up. It comes from the perchlorate ion, which is Cl O4 minus 1 plus 1 there. So the acid, the aqueous form of this is HClO4. Okay. Did we go over those? Did I show you those tricks on how to memorize some of these things? I think I missed out on doing that, didn't I? Did I show you polyatomic ions? ClO3 minus, that's the chlorate. ClO4 minus is perchlorate. One less is chlorite. And still one less is hypochlorite. Okay, so you got a family there with oxygens in it. These are all polyatomic ions and they all have -1 charge. And I always start with this one. And once you know this sequence, you can stick any halogen in there, except for fluorine. Chlorine, bromine, iodine. So you could have bromate, bromite, hypobromite, perbromite. Or iodine, you could have iodate, iodite, hypoiodite, periodite, iodate. Okay, so you got what? 12 of them memorized if you just know the sequence for those. Now, if you're going to make an acid out of them, stick them in water, you need your hydrogen in front. 1 plus balances that minus. So you only need 1 hydrogen in each one. So this 8 becomes ic, perchloric acid. Chloric acid. Chlorous acid, ites become us's. And hypochlorous acid. Okay, so now you got the acids done for the chlorate, the bromate, the iodate, and its family. So you can knock out a lot of them if you just know the pattern. This is the biggest family. There are a couple of other families in there, like nitrate, nitrite, sulfate, sulfite. Let's see. So, do any of those give you trouble? The first one, Al2SO4, taken 3 times. Right? Type 1, type 2, it's type 1, right? Aluminum is fixed charge. So that's why we don't put a Roman numeral in that. How about ammonium nitrate? That's one that has 2 polyatomics. NH4 is a polyatomic, NO3 is polyatomic. NH4 plus, NO3 minus. So they balance their charges with one each. And you don't have to say what the charge is because they're fixed. So it follows the type 1 convention. This one might give you trouble. 68, sodium hydride. We didn't talk about what to do if the hydrogen is not in the first position, but in the second position. If it's in the second position, it's always combined with a metal of some kind. So in this case, the metal would be the positive one, and the hydrogen now would be minus one. In the acid, it's plus, but in the hydride, it's minus one. But you just say sodium, type 1, because it's fixed charge, and then hydrogen becomes hydride. And then we don't say hydrogide. It just doesn't sound right. So hydride is simple enough. And there are lots of these hydrides. And they're always combined with a metal. Okay, potassium dichromate. You'll notice that the only one that has a Roman numeral is the last one, because 10 is in that transition. It's actually a little to the right of the transition, but it's still multiple possible charges. So you do have to say what the 10 charge is. But a lot of the others are type 3s, like carbon tetrachloride. How do we know it that we have to say how many there are? Because carbon is a nonmetal, chlorine's a nonmetal. So it's a type 3 compound. You don't say monocarbon because it's the first one in the group. So it's carbon tetrachloride, which tetra means 4, and you're done. N2O3, dinitrogen trioxide. So you need to know those prefixes that stand for numbers. Mono, di, tri, tetra, penta, hexa, hepta for 7, octa for 8, nona for 9, deca for 10. Those are the only ones you need to know. We got another set to name here. That first one might give you trouble, sodium thiosulfate, except that if you recognize that thiosulfate is a polyatomic ion, then you can look it up. S2O3. I do it like this. SO4, 2 minus, is sulfate. I'm going to substitute a sulfur for one of those oxygens. And it's pretty easy to do. Why? Because look, sulfur is in the oxygen family. So it should fit in for one of those oxygens. If I do that, S2O3, right? I took one of those oxygens, turned it into a sulfur. But it's got the same charge. Now, I started with sulfate, but now I stuck a sulfur in there, and the prefix for sulfur is thio. So now it's thiosulfate. Okay. Iron 3 oxide, we did that one already. Chlorine and oxygen, right? Type 3. They're both nonmetals. Right? Those are the easy ones. Because all you have to do is say how many there are. You don't have to worry about the charge because there is no charge. So dichlorine heptoxide. Cobalt chloride. Cobalt is transition. So you need, that's a type 2. Aluminum hydroxide. Aluminum's always +3. Hydroxide is a polyatomic with a -1, so there's your balance and charge. H2SO3. Now, technically speaking, in order to classify that as an acid, H2SO3 as a sulfurous acid, you would have to say H2SO3 AQ for aqueous. But I'll accept H2SO3. Nitric acid, right? Nitrate becomes ic, So NO3 is nitrate. Phosphoric, 8 becomes X. Phosphate is PO4, 3 minus. So that's phosphoric, comes from phosphate. Acetic acid. You'll probably want to use this one. I just showed you this one. Did I show you that one before? CH213 That's another way that you might see acetic acid. And the reason it's written that way, this is the acidic hydrogen. That's the one that comes off and combines with water and makes the sour taste. But we write it this way sometimes because it gives you a little more structural information. If we write it out, this is an organic compound. The hydrogens are here, the 3 hydrogens like that. Then this carbon is attached to that carbon. And then that oxygen there and that one there, like that. So that gives you a little more structural information. But it's not necessary to pass this course. I just thought it was interesting. But that tells you that this one is the acidic hydrogen, not these 3. So those 3 hydrogens are located right here. And the one that's attached to the hydroxyl down there, that's this one. And the last one, phosphorus trichloride. 1 phosphorus, 3 chlorines, they're nonmetals, so it's a type 3. Law of definite proportions, okay, we can skip that one. Law of multiple proportions, we've hammered that one already. Naming. Which one of these is not likely to form from the appropriate atom? Well, start from the bottom. Sodium is an alkali metal, so yeah, it's a +1. Titanium, 4+. Right? Titanium is a transition metal. And let me see. The periodic table that's given with your exam will be, yeah, it'll show the possible charges for titanium, so you can look at that and say, yeah, that's true. Magnesium, alkaline earth, it's always 2+. Arsenic, AS, it's a pnictogen, so it's always 3-. Or it could be possibly 3-, as long as it's combined with a metal. And then C4+. Which of the following ions is not likely to form from an appropriate atom? All right. Carbon is not likely to form an ion ever, although it does. But it's the least likely. So that wouldn't be a good question because you can get C4+, but it's the least likely of all of them to form. Because it's in the middle. It could go 4- or 4+. Actually go any number of different ways. So that's not a good question. All right. We've done that one before. You can figure these names out. That's nothing big. Okay. I think I've hammered that enough for now. Unless you have some questions. All right. We got 1 hour and 15 minutes. You want to take a break? So for lab today, we've got the graphing techniques. You get a chance to look at it? Not even skim through it? Okay. Have you ever done graphing like for a math course? Yeah, okay. So a lot of this will be old. But what I want to do is the purpose of this lab, even for those who already have some experience graphing, is to make the connection between graphing and experimentation, the results of experiments. Right? Sometimes math teachers will try to connect to reality, and sometimes they won't. So that's what I want to do. Here. Okay. So, yeah, there we go. See, it's recording. Good. All right. So, whenever I'm confronted with a new learning a new skill, I have to know why, because my time is valuable. So if you're going to have to create a graph, then why do we do it? I mean, why should we learn all this stuff? And the primary reason is that when you generate information of a quantitative nature from an experiment, you're trying to convince an audience of your perspective, your interpretation of the data. Sometimes, if the data set is really small, you can just throw the numbers up in a table and talk about them. And hopefully do some statistical analysis to back up your conclusions. But very often, it's both instructive and valuable as a persuasive tool is to create some visual representation. So for this lab, we're going to focus on just one type of visual representation as creating a graph, and we're going to use the Cartesian system, Cartesian coordinate system. Right? So it's only 2 dimensions. Right? So the Cartesian is basically like that. And it's got a point here called the origin, right? Remember that? And it has an x-axis, which we call the abscissa. Oops, I left out a letter. Okay, and we have a y-axis, which is called, don't remember, the ordinate. Okay. So when we plot data on this system, we're actually representing with a single point a value that's associated with this axis and that axis. And the point is where they meet. So if we come out this far on the x-axis and then go up this far on the y-axis, we may have a point out here like that. And if you took this in math class, they probably had you write the value of that point, right? So whatever the x value is and whatever the y value is identifies that point. Okay, in the sciences, this has a special meaning. This represents a measurement. You're making some type of quantitative measurement from an experiment. And you're saying that at least for that one measurement, that's where it's located. But if you do the same experiment again, it might be located here, or it might be located there, or there, or there. That's an expression of experimental error. Error that's inherent in every measurement. Okay? So, for now, we'll just say it's that one. Now, sometimes, before we even plot the data, we may make 4 or 5 measurements and take the average and plot that, because that'll give that's closer to reality. You can take the average of the measurements. Sometimes, very often, researchers, when they plot their data, they'll put all the points up there. So you have just this scattering of points on there, and then you're asking yourself, all right, what does that mean? So it's their job to tell you what it means, convince you of it. All right. So you're, of course, assuming that you got a grid along here and there that's marked off in units, right? We'll talk about that a little more in a minute. But this is your experimental measurement. Now, by convention, the X values that you put on this are independent variables. That means that the experimenter has chosen that value. So when the experimenter chooses that value and plugs it into the experiment in some form or fashion, then the experiment responds and kicks out a dependent variable. So what you're saying is independent, dependent identifies your point. For instance, if we were to say, all right, I've got a confined gas and I'm going to put it under pressure. And I'm going to apply a certain amount of pressure here. Well, the gas responds by giving me a volume that may be here. So pressure volume, PV, XY. Okay. Let's see. I'm trying to follow along here with their discussion so it's easier to make sense of what I'm doing. Okay. We can now plot our data as independent, dependent variables. And I'm going to make some more room. And let's say, for argument's sake, that we come along here and we've got one there, one there, one there, one there, 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 and one there, maybe one up here. So what that looks like is, as X increases, Y increases. Oh, by the way, this Cartesian system, everything on this side of X is positive. Everything on this side of X is negative. Y is positive here and negative here by convention. Now, we typically in the sciences tend to stay in this positive region, but these are available if you need them. So what do we got here? Well, that's not right anymore. As X increases, Y also increases. Right? That's called a direct proportion. And in this case, maybe we think, that's pretty close to a straight line. It's not exact, right? There's experimental error. But we could draw maybe a line that minimizes the variation from the line to each of the points. And that's what, my mind's going blank. That's what we do when we draw a best fit line or a best fit curve to the data. So you get a straight edge in this case because it looks like a straight line, and you lay it over there, and it's probably better to use a transparent ruler so you can see the points that are underneath the ruler and minimize the distance between the line and the points. Right? You won't get it exactly because look, they're scattered, but maybe we go like this, like that. Maybe that would minimize the distance between the line and the points. So that's our representation for this data. Maybe you've got places on that line where you actually have data points. Right? That would be good. So how do we represent this line in mathematical terms? Straight lines are good. They're very well behaved. Remember this formula? Remember that one? Okay. That's the formula for a straight line. Right? Y, the variable y, is equal to some constant value times x plus another constant b. But they have special meaning here. This is what? The slope of the line. This is y-intercept. Exactly. So our data only covers this much room. So the y-intercept, you have to assume that it's that. Or if you want to look at anything up here, you have to assume that. If you want to go back to that line in the future and say, all right, what if I had done X here? Right? There's no data point there. But if I did, it would give me a Y like that. Anytime you do that, this is called interpolation. And you're reasonably safe interpolation because you're bounded by real values, real experimental measurements. Outside the measurement data, you're extrapolating. Oops. Okay, and then you're getting into murky water because you don't know what the line does after that. It could go like this. It could go like that. It could reverse. Who knows? So extrapolation is a little more hazardous than interpolation. All right, so we've got this line and we want to represent it. And what I'm trying to do is give you lead into questions that are asked in the procedure. They want you to determine the formula for it right here. They want to put value in here and put value in here and say, that expresses this line. So how would you do it? Well, the slope is what? Rise over run. Right? A change in Y. And we would do maybe say from here. That would be ideal because you actually have a point that's on the line here and a point that's on the line there. If that's available, use it. So you would measure what's the difference between this Y and that Y. That's your change in Y. Okay? And between this X and this X, that's your change in X. So now the slope would simply be that measurement of change in Y divided by the change in X. Okay? So what would the units be on that value? Right? Because these probably have units of some kind. Right? The units of X down here and the units of Y up there. And remember, whenever you have a number that has units with it, when you enter an operation, the units go with it. The units enter the operation too. So say if this one was, let's go back to pressure. If this pressure was in atmospheres and this was in volume was in liters, okay, then it would be liters on the top divided by atmospheres. So whatever value you got here would have units of liters per atmosphere. Right? And that would go right in here. So now we have a value for slope. So how do we finish the calculation? Well, the simplest way is put the slope in and then find a place on the curve. If you have a data point that actually is on the curve, use it. Put the Y value in here and the X value in there. And then solve for the unknown. And that'll give you your Y-intercept. If you don't have a point that falls exactly on the line, then you would have to measure one to do the slope and then use one of them to give you the Y and X value and solve for Y-intercept. Then you report it with a real value here and a real value there and your unknown, your variables here as, I don't know, volume and pressure in our example. Okay. That's how you would express that line. And if you're going to publish this in a referee journal, you would probably scatter your points, draw your best fit line, and put that formula next to it, plus some other statistics, which we don't have time to go into right now. I don't know. Has anybody had any statistics out of this? Nice. You probably touched on it in math, like the mean, maybe the median, possibly standard deviation. Talk about that. Okay. Those types of calculations. Then you might want to put them in there. There's also an R-square value, which you probably didn't talk about, but R-square represents how close is that group to a straight line of all the scattered values. The closer it is to 1, the more likely it is to be a straight line. So sometimes you can get 0.987 like that. Sometimes I've seen research papers claiming a straight line when their R-square value is like 0.6. So I think they were stretching it that way. Okay. So that's what you do with a straight line. And this is a direct proportion. So it would be an inverse proportion. An inverse would be, this is a positive slope. Inverse would be a negative slope. Right? So the inverse would go that direction. What that means is, as x increases, y decreases. So the change in y is negative as x increases, and this calculation would give you a negative value. Okay. But, there's always a but. We don't always have straight lines. Yes, let's start fresh. Sometimes your data looks more curvy than it is linear. So let's stick to the positive quadrant. So we've got some x here and some y there, and there's your origin. And sometimes we get curves. A good example is Boyle's law, which we haven't got to yet, but we will. Boyle's law says that the pressure of the gas times the volume under those conditions is equal to a constant value. Okay? So you can see from the formula that if this is constant, if that goes up, this one has to go down to keep that constant. And vice versa. If that goes down, this has to go up. So that means that we're going to have a negative slope, except for this particular plot, it's going to look more like this. It's going to curve like that. And if we draw a best fit for this, we can't use a straight edge. Well, if we used a straight edge, it would be a different slope depending on where we were. Like that. Okay, it's a changing slope. So how do you draw a best fit curve for that? Well, if you're good freehand, you could probably do something like this. Or if you have a French curve, then that helps, right? Everybody know what a French curve is? Usually a piece of plastic that's got a changing radius curve, right? So it would look something like this. Like, maybe something like that. I don't know. So really, a large radius curve here and a small radius curve down here. So you just move it until it fits, and then you draw it in. And you might have to move it several times to get it to give you a best fit. That's good for looks, but unless you know it's this relationship, you can't write a formula for it. I mean, I've seen scientists try, and very often what they resort to is polynomials, which is kind of a cop-out. Because a polynomial with enough powers, terms in it, can usually mimic any type of curve. Okay, so what do we do with that? Well, one of your questions in here wants you to plot just that type of data. And it's a nonlinear relationship. Figure 3 on page 19 is the example. By the way, this curve has a special name. I gotta refill my drink so I can keep talking. Any ideas? It's called a hyperbola. Hyperbolas have an interesting characteristic. This tail here will never touch the x-axis. And this tail will never touch the y-axis. Right? Think about it. If this represents that curve, then what would happen if this touched the x-axis? What would the value be for y? Well, let's be consistent here. This is pressure. Nope, excuse me. Nope, that's not pressure. That's volume. And this is pressure. Okay? So, if this one touched the x-axis, what would y be? What would v be? No matter how big this is, if it touched the x-axis, that means this one is 0, right? And it could never equal that constant because 0 times that is 0. And the constant has a real value, right? Same for the other. If it goes the other direction and touches that, then p becomes 0. Right? So that means that this curve will never, ever touch the axes, no matter how far it goes. Okay, so scientists hate curves. They get rid of curves and replace them with straight lines whenever possible. Take your data and manipulate it to produce a straight line. It's very common in chemistry, particularly biochemistry, for transformations of data to be made so that you can generate a straight line. This one is one of the easier ones. If you take this formula and you do a legitimate mathematical transformation, in this case, we're going to divide both sides by b. Right, we can do that. Now, that cancels out. It's equal to 1, so we're left with p. Right? P now is equal to k divided by b. But what I'd like to do is pull my terms out from one another. So I'd like to leave the k here in the numerator, just like it is there. And I'd like to pull this v out. So what is it equal to when I pull it out? Right, 1 over v, correct? Okay. So now look at what we got. We got y equals mx. We got a straight line. All we have to do is take the inverse of all of our volume values and replot them with a different axis here because the values are going to be different. So you have to plot them differently, just like they do in that example. And if you do that, you get a straight line. But notice there's no b. Right? So what's b? B is equal to 0. The y-intercept is 0, which means it starts at the origin. That's the transform. And now, rather than v, we have 1 over v on this axis. And that's how you get a straight line. With this data. Okay. Now, what are the units of measure? Well, let's see. It looks like they use their atmospheres for pressure, and volume is liters, right? Looks like that's right, liters. What would the units of measure be on the axis after you transform it? Well, if this V is liters down here, what is this whole thing? Well, liters is in the denominator, correct? So now the units of measure becomes liters to the -1. I bet you thought you'd never be using negative powers again that you have to use left math class. Yeah. So the units of measure are liters to the minus 1, or reciprocal liters. Okay. Now, if you plot it, you can get X is 1 over V with those units, and you can say Y equals the slope, whatever the slope is. Right? You can do the slope again, just like we did before. But what are the units of measure for the slope? Well, it's going to be a change in Y divided by a change in X. It would be liters to the minus 1 divided by atmospheres. That's a little difficult to print. So this is also equal to liters to the minus 1 times 1 over atmospheres, which is the same thing as atmospheres to the minus 1. So liters to the minus 1, atmospheres to the minus 1 is the units of measure for the slope. Okay? Am I losing, folks? Okay. Now, if you want to go back, and if the question is, what pressure, if you're using a straight line, it's easier to interpret a straight line. It's easier to draw a straight line. So if you put your data in a form of a straight line, it's easier to, interpolate. So if the question is, what would the pressure have to be to give me a volume of X or Y? Well, if you're using the straight line, you can't just take that Y volume and look on it here because it's not there. You have to take the reciprocal first. The reciprocal of the volume that's given to you. Say it's, I don't know, 10 atmospheres. So then you would take the reciprocal, 1/10, 0.1, look up 0.1, then go over to the straight line and find your pressure. Okay? You got to remember that you made the transformation. So when you're looking for the data, be sure the data is in the proper form to use your graph.
Are you want us to fill out this whole thing?
Well, there's a bonus section here. Right. It starts, let's see, required section goes through, let's see, there's number 9 in its subsections. Right. So I think you're going to have 3 graphs to draw. One is volume temperature. The other 2 are pressure volume and pressure inverse volume. Just like I showed you here. The bonus section is, the first section is the titration curve. You can draw it if you want, and they give you an example of a titration curve here in the beginning. It looks like a sigmoid, like an S. You can do it if you want to, you don't have to. It's a bonus. Or you can just go in and see, maybe you can answer the questions without drawing the graph if you don't want to do that.
What do you want us to draw the graphs on the main portion? Do you want us to do it in our books or like what?
No, not for this one. This one, you're going to do everything, answer questions on the form or separate sheets of graph paper. And I've got extras here. You may want to take a few of them. There should be maybe 4 built into the method. That may not be enough if you want to draw some more. So take a few sheets. Yeah, and then when you turn in your work, just attach the graphs to the back of it.
Turn it next week.
Yeah, next week. Oh no, you got 2 weeks because we don't have a lab next week, right? Right. So you got till the following week. Next week I'll hand out the lab that we're going to do the following week, so you can get prepared for it. I don't want to give it to you now because it might interfere with all this work. And then, but if you're curious, it's on Brightspace anyhow. Let's see. Okay. So that's all I have to say about that. Was there something